All right, thank you very much for coming to the talk. I think this is our second physical talk in the whole year, so it's quite a good thing to really physically meet everybody. So let me introduce our speaker a bit today. So Edmond Ho is currently an associate professor and also the program leader of computer science in the Department of Computer Science and Information Science at Northumbria Universities. Which is actually quite close. It's in Newcastle, so it's just like 30 minutes drive from there. So yeah, and before joining the Northumbria University, he was a research assistant professor in the Department of Computer Science in Hong Kong Baptist University. He received his PhD in the University of Edinburgh, and his research is about computer graphics, computer vision, motion analysis, and machine learning. So personally, I know Edmond for like 20
We are not
years.
that old.
It's at least 20 years that we know each other.
Around 10.
Yeah, okay. So over the years, I found that Edmond is super hardworking and super eager to interact with people. And he is very good at communicating with his PhD student, giving a lot of care and support to his PhD students. So that also explains why he has a lot of high-profile publications coming out in the past few years. So I'm very happy that he come to join us today and give us a talk today. So without further ado, we'll probably pass the floor to Edmond, and please feel free to start.
Thanks, Hubert. So good afternoon and welcome everyone. So this is a very special experience after how many years? I think 3 years. So my last in-person, face-to-face research seminar was 3 years ago. Yeah, back in 2019. Obviously before COVID. So this is a good chance for me to meet with you again. So well, while I'm spending my 6th year in the Northeast, and I also spent another 3 or 4 years in Scotland before, I've never been to Durham University. So this is my very first time to be here. So I visited Durham 10 years ago for a wedding, so probably Frederick know which wedding.
Yeah, I was there as well.
Yeah. So I attended a wedding, but not having a chance to visit Durham University. So thank you very much for the invitation, and I hope you enjoy the talk today. So as you can see, it is about something about more on the medical side. So this one, I would say, not super technical. The content, it may not be super technical because I attend some of the seminars in this series before. I know that some of them are very technical, but I would also like to share with you our experience in engaging with, for example, NHS clinical partners. So share some sort of experience sharing, and feel free to make it as interactive as possible. I would say it is not super formal. I don't know whether Hubert and will agree, but let's make it more informal, more interactive. Feel free to interrupt me anytime. So as Hubert mentioned, I'm currently an associate professor, and I mainly work on computer graphics, computer vision, and which is related to machine learning as well. So in recent years, and I'm also the program leader for the undergraduate program. So yeah, so this is a brief background on what we are going to talk about today. So basically, I will briefly introduce the background, the related research in this area, the early prediction of cerebral palsy from motion, basically from video, from basically just observation of the baby's movement, and then we will try to analyze whether the baby is at high risk for CP, cerebral palsy. I will go through about the lengthy, I shouldn't say lengthy, but very interesting process for data collection and ethics. So just because I'm not sure how many of you have a chance to work on this ethics approval with NHS before, so I think I can share some of the experience with you. And then we will talk about the methodology and some of the recently published work. So commercial time before I start. So I was invited to give a talk at an event to be organized by the Royal Society of Medicine in July. So if you are interested, well, unfortunately, we have to pay in order to attend the talk. But I would say today's talk will be quite similar to that one. This one will be slightly more technical. That one will be more on the medical side or on the future. Potential future development, because I have a check on the program list, so I will be the only computer science guy there, so all the rest will be medical people. So it will be very exciting, and also not sure what will happen. So wish me luck. But if you are interested, feel free to register it online. And I'm not sure whether they will share the video. So it will be also a hybrid event. So it will be held in London, but they will also broadcast it online. So if I receive more information, I will share with you all. Time. Okay, so background and related research. So first of all, the team. So obviously, without the whole team, this project will not be able to continue. So Kevin is my PhD student. So he just defended his thesis at Columbia recently. So he will probably likely get his PhD in July. So actually, he passed the final. So we're just submitting the revision. So we have two main NHS collaborators. So they are Claire and Nick. So they are super helpful, super passionate about how to use computer science, machine learning to help their clinical routine. So Claire is a physiotherapist, which is mainly looking into this, how to analyze potential risks of baby from body movement. Nick is basically a very experienced professor, so clinical professor. So he also the head of the neonatal ICU. So they take care of a lot of baby at high risk. So they have a lot of experience in doing research. So Hubert obviously is also a valuable member. So because Hubert was the second supervisor of Kevin when was in Northumbria, but obviously we continue the work together.
I had more hair in that photo.
Well, I try to use the older photo, that's why. That's one reason. Okay. So and we also have some recently joined members. So well, for sure I can't include everyone, but Mani is also our supervised student at Columbia, and okay. So he is also recently joined the team to work on the data and this problem. Okay, so background. So CP, what is CP? CP is basically it is some problem which is affecting the movement of the person if they suffer from it. It is more like there is some development issues at the brain in the brain. So it is sometimes it may be because of when they get it before birth or during the process. So it is very difficult to basically to be treated. So basically, I would say we are trying to have early intervention rather than later. So sometimes I still remember, well, yeah, before COVID, I was invited to a neonatal meeting, also at Durham, but not at the university. It is a regional clinical meeting, so they asked us to again present our idea of using computer vision, machine learning stuff there, and they told me that sometimes they have some patients diagnosed CP at the age of 16 because too late. So it is just because the parents do not realize there is a problem going on when the kids are not moving in a typical manner. Okay, so this is very important. And when you talk about how often you will see or how often you see a baby having CP, it's around 1/400. So this is the statistics. And in the UK, so around 1,800 babies will be suffering from this per year. So what we want to do is to see whether we can use machine learning, computer vision to do this. So obviously, diagnosis. So today I'm not talking to clinicians. So, but when I talk to the clinicians, maybe I have to be more careful because there is a debate. So what is the best way to diagnose CP? So from my understanding, it will be MRI, more in-depth diagnostic tools rather than computer vision video. So I would frame our work to be a filtering, prediction, rather than a hardcore diagnostic tool. So we are going to identify babies at high risk, which is related to CP, rather than we say, okay, we have a pure diagnostic tool But for sure, here the contact is we try to help the baby, get the baby, for example, to take MRI further analysis. But obviously, we can't afford to take all the babies to do that, right? So we have to filter out, find out the high-risk babies to get them diagnosed. So what is GMA? So GMA is one of the tools that we can use it without any very complicated diagnostic tools. So GMA is general movement assessment. General movement, basically, that means random movement. Obviously, you can't ask a baby to move in a way that you want to follow. You can't ask them to do a star jump or whatever. Okay, so that means we are going to look at the baby. Their normal movement just when they are relaxed. So what will they do? And we try to see if they are having or developing typically. Okay, so I have a video basically download on YouTube to explain about GMA. So you can see these are more typical babies, but obviously when we highlight that one, you will see some atypical pattern. Maybe some limbs are not moving a lot. But in general, you will expect that a baby, if they are developing in a typical manner, they will be moving randomly all the time. So that's why we are trying to see if we can use this sort of techniques to identify babies who are in higher risk. Okay, so but this GMA, you have to do it at a very timely manner, because at different stage, you know that, well, for babies, they learn everything new every day, basically. So we have to compare to the larger cohort, what would be the typical development pattern. So for this GMA, usually we are talking about looking at week 12 to week 20 of the baby. So which is roughly 3 to 5 months. After that, the GMA will not be accurate because they are a little bit bigger. So they may learn more. So you cannot really use a standard development cycle to assess whether the baby is at high risk or not. So basically, you put down the baby and then to take a video or use a human observer, the assessor, to look at the movement. We mainly look at the fidgety movement, plus or minus. Plus means present and minus means absent. So basically, to see whether we can see this pattern. We also look at the complexity, variability, fluidity of the infant's movement. So it is quite easy to understand, okay, we may be able to find some pattern, discover some pattern for these analysis. So this is also another paper published last year, more on the clinical side. So this is what they use as a GMA assessor. So just to remind you that nowadays, still we need clinical experts to look at the baby or look at the video. So it depends. Obviously, under COVID, we have to self-isolate, so people may send the video to the clinician to have remote diagnostic sections. So what we call remote GMA. So this is the form they are going to take. You can see some of them are quite intuitive, like the direction of movements varies, so it is about the variety. And some of them are about the speed, the smoothness of the motion. Some things are very difficult to interpret. Movements are too rigid. Yeah, so these, you can see this requires some sort of experience and maybe subjective to the assessors. So obviously, you need to have very experienced clinicians, or more specifically, GM assessors, to help you to assess the baby by watching this video or looking at the baby. So these are just like other labor-intensive jobs. So it will be very difficult to scale up the process. So for sure, we are not the first one to work on this. So some researchers started to look into this back in year 2010. So they tried to use some very rather traditional computer vision techniques, pattern recognition, and is to try to analyze the variety of the movement. So they basically just find the difference between the picture, and then they will highlight the pixel. This is like trying to see the history of the movement, and then they will calculate the ratio the active pixel versus all the other pixel, and then they will have some measurement to see how much the baby has moved over time. So this is a very simple way to do it, but it is 12 years ago. So 2012, they start to use something like optical flow, and then with some classifiers like SVM to try to classify whether the baby is normal or abnormal. So usually abnormal means high risk, normal means low risk. But obviously nowadays we do use more deep learning, right? So this one published last year, 2021 in JBHR. They use SDGCN, basically start to use graph convolutional network. So there are some work in between, but to be honest, not that many. A lot of them are just repeating the use of the previously mentioned handcraft features. And this one is slightly more different, so that's why I picked this one. SDGCN, so they try to compute the joint representation. They use post-based information. So these are basically the trajectory of the joint, and then they try to cut the long video into short clips and try to find out which part is potentially having problem. So they also use attention mechanism to try to highlight which part is likely to contribute more to the classification result and likely to be problematic parts. So as you can see, this is their proposed visualization. So the rows are the joints and the columns are the clips in the whole video. So you will be able to see at which moment, which body part is showing some atypical pattern. Okay, so this work is done in Australia. They have a pretty large data set, something like 200-ish video. So data collection, it is mainly about our project in the Northeast, okay? So we initially have some contact with, as I mentioned, the neonatal ICU at RVI. So RVI is located in the city center in Newcastle. So we learned that they previously have some other research more on the clinical side. So they just take the video and keep it for GMA assessment later on. They are not intended to use it with computer vision or machine learning stuff. So they already have 200-ish videos there. So we were wondering, can we do something with this? So we start to talk with each other and try to come up with a plan to get the ethics. So obviously, when you try to use the data, it is very difficult to go to NHS every day, and they have their own system. So easiest way is to transfer the data to our uni, and then we can play with the data. So, but it's a very lengthy process. So you have to submit the application through IRAS, what we call Integrated Research Application System. So this is basically you submit the application, and then the application will be reviewed by this REC, and then finally will be approved by the relevant authorities. So which is the HRA. So it is a super complicated process. So I'm glad that my student Kevin has been leading the process, rubbing the stuff with me together. So it has to be including the research protocol. It is more like the study design, the cohort, the sampling, and then how to manage the data, and so on. A brief outline of the methodology as well. And you have to do a lot of other documents like the sample consent form and participant info document. So because we have to get the consent from the parents again, we have to change the usage of the video recorded at RVI. So our clinical partners are super helpful. So they call each of the parents and try to get the revised consent to let us to use their data at Northumbria. So, but for sure, getting the consent is the other part. So we first need to get the approval from the NHS and related ethics. So it's like a mini grant proposal, I would say. So once, as I mentioned, once we get the ethics, we can start calling the parents to get the consent. So this is obviously I skipped that part. And then we finally get our data set. So why it is called 38? So obviously we so far collected 38 videos only, because we have to get the consent one by one. So our clinical partners are still working on it. Hopefully in the future we can further expand the data set, and there are some new cases receiving every day or every week. So we hope we can expand the data set. So this is the video we have collected. So it is in the real world clinical settings. The patients, the babies and the parents are really going to the routine clinical checkup before COVID at that time. So I learned that during COVID, during the lockdown, they use a smartphone app to take the video and send it over. Okay, we are also finding out whether we can access those videos in the future or we can be part of the study. We have clinical partners, so they help us to annotate the data as well. So basically, divided into two types, normal and abnormal. FM plus is having the fidgeting movement, and FM minus is not having. So at the end, it is as expected, a super imbalanced data set. 32 videos are normal, 6 of them are abnormal. But we are already at a better position because for REI, they usually receive some high-risk baby, which are preterm. So they are higher risk to get this. So this number, this ratio is already better than a normal distribution, I would say. So in addition to or before the RBI 38 data set is, to be honest, we received it early last year, 2021, in the middle of 2021, we got the data. But before that, so we have been trying to explore whether there will be some data available somewhere. But obviously, these are very highly sensitive data. So a lot of people just publish their result without sharing the data, or they cannot share. So luckily, a group in Germany, they create something called a mini LGBT data set. So they published this paper in Vika in 2018. So their idea is, again, they know that people will use, for example, video for GMA. So they want to see what's going to happen if they use, for example, that camera, Microsoft Kinect, to record the video and then reconstruct the movement of the real baby using this 3D generated model. So they call it SMILE, SMIL. I don't know whether I pronounce it correctly. But if you work on 3D human body shape reconstruction, you will know there is another model, simple as MPL. So SMIL, SMILE, is basically a variation from this for babies. So they will be able to generate the baby, and in this paper, they basically do not have automate assessment. They just reconstruct the 3D baby and then ask the GM assessors to see whether they will find there is a difference between looking at the real color video versus this 3D reconstructed baby. So from that study, so as far as I remember, there's no difference, and that's why they published this one. And later on, this paper is extended to a PAMI version. So we got this data set. They have 37 infants in their study, and finally they shared 12 of them. The CG rendered video as well as the 3D information. So what we have done, well, sorry, I played this video before. So basically, they are trying to do this. So obviously, they don't come with the annotation. They just share the video. So I ordered our clinical partners again, asked them, can you look at the video and help us to annotate? And they kindly help us to annotate such that we can have something to start with back in 2019. So again, we mainly annotate the baby whether they are normal and abnormal. So out of the 12 videos, so 8 of them are normal and 4 of them are considered as abnormal movement patterns. Okay, then this comes to our research, our project. So basically, we want to see How we can make use of this, as you can see in the previous work before, well, we started this back in 2019. So before 2019, there is not much research related to pose-based features. They usually use image features like optical flow and so on. So we try to see whether we can do something. So pose-based, because my background is more on motion capture, so I know how easy to model these skeletal movements. So it is very intuitive to try to get the pose estimated position, the joint position from the video, and then we can try to extract some features accordingly. And this is also some of the work that we found back in 2019. So they are not doing any automated assessment at that time again. So they just again convert the video to this skeletal motion. So this is from open pose. Why they have to do it? So obviously, sharing the video over the internet is very problematic. You may be end up with some privacy issue if, unfortunately, your network is being hacked or some other reason. So they think just like the previous 3D motion rendering. So they try to see whether we can replace the video with something else while we can enable the TM assessors to do the remote assessment. So this one, again, this research is again, they try to ask the assessor to look at the skeletal motion only instead of the raw video. So we use the same open pose library to help us to extract some important joints. We picked 15 joints only. We didn't use the face landmarks. And also the fingers, we discard those as well. Okay. So data preprocessing. If you look at the video demo in the last slides, you will find that there's some discontinuity, sometimes due to the movement, sometimes due to the self-occlusion. So obviously the extracted pose will not be perfect because it is on a frame-based basis. So but what we are talking about is a temporal sequence motion, the joint sequence. So we have to fill in the gaps for some of the frames. When you use open pose or similar pose estimation algorithms, usually they will give you the location of each joint as well as a confidence score. So how confident the estimator will think. So if it is in lower confidence, we may discard that information and interpolate the motion accordingly. So we try to fill the gaps. So you may say, yeah, we added the data a little bit, but empirically, it doesn't make much difference. It is improving the results. And we finally add a filter to smoothing the joint trajectories. Okay. Good. So feature extraction. So what sorts of features do we need? We have the pose, but can we make it easier? So we call that we have the checklist. So basically, we can see some of these items are related to, well, I just make a very rough categorization. Some of them are related to the variety of the movement pattern. Some of them are related to the smoothness of the movement. So can we model these sorts of things using some handcraft features based on the pose? As a very early preliminary work, so we proposed some histogram-based features to try to capture the variety. For example, the joint orientation, which is basically the bone, the orientation of the bone. So essentially, if you say a wider variety, that means it should be more evenly distributed in different orientation. So joint displacement is more related to the velocity. So whether you stay in a particular velocity or you keep changing. So this is an example of the orientation-based histogram. So we can see an abnormal samples or the baby, which is labeled as abnormal movement pattern. So it will be less evenly distributed, while the normal baby is more evenly distributed. So we can see this pattern very easily by using this sort of features. And for sure, we further propose some other features in our latest work, so published early this year, relative joint orientation and relative joint displacement, because some of the criteria are related to the coordination of different body parts. So we try to see the interaction between different body parts on the baby. And we also apply some frequency analysis to see whether there would be any repetitive pattern in the baby's movement. So because we focus on the feature engineering or feature extraction in this work, so we just use some traditional classifier at this stage, and we try to use the one-out force validation. So because we have a relatively small data set, so we just have 38 motions, and this is the result we published early this year. The bottom 3 rows, so you can see we achieved pretty good results on the super small mini RGB data set. So mini RGB data set is the one we construct using TNet data, the depth camera data, the 3 reconstruct. So again, the baby movement are real. It is just the rendering is not. So they try to hide the identity of the baby such that they can share the data online. So there are some other methods as well, including deep learning, non-deep learning methods. So we achieve perfect classification. So this one will be more interesting because this one is the real world data set we collected from RBI. So you can see a general drop in the performance in all cases. So obviously this one is slightly larger data set and also more challenging in the real world setting, but we still managed to get a pretty good high accuracy. So basically just one motor is classified out of the 38. So as you can see, some deep learning methods are not doing as good as ours. So the next one is, okay, we can say yes or no, but what else we can do? So we may want to make it more interpretable. So it is, we believe it should be useful for the connection as well. And we have some initial attempt on this one. So we also published this last year. So we again try to use deep learning network and try to use channel attention to find out which joint, body joint is contributing more towards the final CP prediction, such that we can estimate which joint is more problematic. So maybe the clinical expert can look into that in those areas in more detail. So this is the result. We just tested on the mini RGB data set because at that time the RBI 38 was not available yet. So we tried with the smaller mini RGB data set. So it was the best performance at that time, but obviously early this year we can get 100% classification performance. And these are the attention values for all the joints over the 12 validation. So we can see usually the limbs are contributing more as expected in the baby movement. So the baby fidgeting movement usually appearing on the limbs. So we do quite a lot of things on interpretation, interpreting the results. So we also try to have more visualization. I will talk about this in a minute. So again, we try to find out which part is contributing more, is showing more. So we try to propose some other visualization techniques. So this one is slightly different from the previous method because we mainly use LSTM to model the trajectory of each joint. So this is the body part specific branch. So we use 1D convolution first to process the joint position sequence, and then we try to use LSTM to model them. And finally, we try to calculate a contributing score for each joint. So I will show you a video. So like this, we try to calculate some scores, and this one is normal baby. Well, this is from the mini RGB data set, so they rank the baby using this CG character. The motion is captured from real baby, and you can see the arms are moving quite relatively more, so the score of the arms are higher from computation. So by the way, I'm personally do not like this visualization a lot, but we propose another visualization to be demonstrated in a minute. But one of the reviewer didn't like it and keep asking, why don't you just show the numbers? Okay, the reviewer claimed to be some clinical background and say, oh, it may be easier for the clinician to look at it. For me, not necessarily the best way. Anyway, yeah. So on the other hand, we have an abnormal pattern case, so we can also see some of the values will be different. So again, this is purely based on the machine learning result. We haven't verified by clinical expert yet, so I will add a little bit more information. Okay, so finally, I promise this is the final one. The final one will be, well, to be honest, I personally like this visualization more because I'm a graphics guy. So I want to have more visual stuff rather than just look at some numbers. So this one is basically, we have an image frame. So we do segmentation. We compute the segmentation mask using the state-of-the-art from computer vision community. So we can segment different body parts like this, so you can see different shades of the color, so for different body parts. And this one is for visualization purpose only. So the mainstream classification is still the same, similar to the previous one. We have some arm limb-based feature extraction. This one is slightly different from the previous work. Previously, we just treat the whole video as a single one and we extract the features. But this one, we will segment the motion into smaller windows, and then we just should try to locate when and where the problem is. So similar to, in the sense that it is similar to the concept of the JVHI paper in 2021, because we published at the same year. So at that time, but the concept is quite similar. We try to chop the video into different parts and then locate the problematic part accordingly. Okay, and then once we classify which short video clips is considered as abnormal, so we can visualize it by coloring that part accordingly. So this one is mainly, I would say, for visualization. And I can show you the video. So you will see sometimes the segmentation mask is not perfect. So it is coming from the method we adopted, I would say, because we didn't change anything, so it is imperfect. That's why in the previous one, we submit this paper somewhere before, and that's why the reviewer say, oh, the segmentation box is not perfect, so it can be distracting the clinician, something like that. And then say, oh, why don't you show a number to make it easier? So you can see sometimes the segmentation box is not perfectly identified. But this is the first attempt. I would say we try to make use of this technique to highlight which body parts is more problematic, so easier for the clinician to look at where it is. Having said that, when we show this to clinicians, the small number of clinicians I met, so the comments are somewhat mixed. Some of them like it, some of them may focus on, oh, it seems like they highlight some wrong area at wrong time. So this go back to the problem, because this is purely showing what the machine learning thinks, what the model thinks, rather than ground truth. We don't have ground truth. I forgot to mention that we just have a single label for the whole video, normal, abnormal, but we don't have ground truth annotation on when and where the problem is. So this is something we have to do in the future. Can we have finer level of annotation, or can we keep the clinician in the loop to help us to verify which part of the visualization is correct or not? Okay, so perfect timing. So conclusion. So basically, this is our very first attempt. So you can see why I used two words, blah, 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 at the very beginning. It is still in progress. I will say it is a completed project. So, but it is the first few articles we published based on our engagement with NHS clinical partner. There are quite a lot of stuff to do. For example, better way to locate the abnormal pattern temporally. So we mainly looking at the spatial feature. But what about temporally? So how to better visualize the result, as I mentioned. Yeah, reviewers, clinicians, some of them like it, some of them don't. So how to get better way to visualize it. And also we will need to verify more by the clinical expert, especially if we are trying to guess some of the abnormality. Okay, so any question? That's pretty much from my side.
All right, great. Thank you very much for the talk. Any questions from us here? Yes, go ahead.
Yes.
So as you have made a very serious ethical growth with the NHS.
Yeah.
So normally how long will that take?
That's a good question. So I checked the date again. So my student started in March 2018, and we got it. You can see the letterhead. We got the approval in May 2019, so not so bad. I would say, obviously, my student spent a few months before submitting the application. As far as I remember, he should have submitted it in September or October in 2018. So roughly 6 months for the approval. In the middle, we were asked to revise the application once. So it is not too bad, but I think we have very strong support from our NHS partners. So they work with Newcastle U and also Newcastle Hospital Trust to do some process to help us to coordinate with us basically, because we have to ask them to support us on something. And then we have to basically submit it together. And also Northumbria will also have the support team to help us to sign this document on behalf of the uni. So it is not on individual basis. So while I am the PI of the project for this ethics, I still need to have the sponsor. The sponsor will be Northumbria Uni. So you need the university support. So you can see, and also the Newcastle Hospital Trust. So there will be 4 to 5 organizations involved in the process. And after that, we get the ethics back in 2019. So it took us another 2 years to collect the data because of the consent. We have to ask the parents one by one to get the consent. So this is another lengthy process. Yeah. Yeah, that's why I guess this is not something people will talk very often in the research talk, right? So usually we use open source data. So you just need to do the internal ethics approval. I think yeah. You don't need to do this external one. External one is super lengthy. So if you want to do something, start
Start in the beginning of your PhD, otherwise it will come after you graduate.
Yeah, so Kevin, in the sense that he because COVID, we extend a bit the university support student to extend a little bit, so that's why we can complete the study. So we were a bit lucky or unlucky, I don't know which side, but anyways, he can complete this work before graduation, so which is good.
So at some point, you mentioned the work from the German team that showed that the 3D reconstructed baby, when presented to the clinicians, there was no difference in their ability to distinguish if there are signs of the condition. When the same thing was done for the skeletal information, was there any difference? Were the clinicians able to use just the skeletal information without the?
Yeah, this is a very good question. Actually, when we show the skeleton to our clinician, they like it. They say, "Oh, it is amazing." But on the other hand, when we look at the criteria, so there will be something related to rotation that we check. Sorry, again, we'll be able to find it somewhere. So they did highlight, sometimes they want to look at the rotation. But obviously, it is not clear. If we don't have fingers, you can't see the rotation on the 2D extracted skeleton. So that's why they do think, oh, something they want to see more, like torso rotation. So these cannot be visualized purely by the 3D skeleton. Yeah, so from my point of view, it may not be perfect to just look at the 2D skeleton. But on the other hand, the German team, the 3D body, you can see a lot more. Yeah, this is a very good question. So let's see where somewhere, yeah. 50.
Oh, yeah,
Yeah,
very good eyesight.
rotation. Yeah, yeah, they do have these criteria. So and our clinical partner pointed out to us, oh, maybe it's missing. So that's why we want to see if fingers will help. Because fingers may help you to understand more if there is any rotation. But it also depends on the resolution of the video or how accurate you can extract those stuff.
So there's also a question online as well. Yeah, well, don't forget we have online attendance as well today. So it's about the visualization part of the abdominal joints. The question was about like whether it would be a better visualization scheme, say using a gradient color to visualize how confident the prediction model is, instead of using a solid generic solid color or other schemes at all.
Yeah. We tried it a bit. This is a very good question. So you may remember I have the numerical value based paper before the segmentation based. So we use different intensity to reflect the value of the number. It's just one of the reviewers didn't like it and asked us to change it to the number. And then because for the second work, we just have a binary classification result. So we use a solid color. But this is definitely something we would like to do, and this is really providing more information, how confident we believe this is an abnormal or normal part. Yeah. Yes.
From your experience, can you briefly compare the machine learning based method and
yeah.
And can you briefly compare them?
What do you mean by?
What do you think? What do you think the advantage or disadvantage?
All right. So obviously we start with non-deep learning methods because we start with the 12 videos only, the mini LGBT dataset. So at the very beginning, when we start this work, we were focusing on, well, Kevin was focusing on the ethics approval. So the first year, basically, we focus on the ethics approval and start to do this post-estimation stuff, try this post-estimation stuff to see whether this is really useful. And then we start with the machine learning based method, mainly because we have very limited data. So you can see while it is maybe nowadays mainstream is deep learning, so we still outperform the deep learning based method on this real world data set. I'm not saying they are not good, but they need more data. Maybe they designed with, like I mentioned, the STAM as the STGCN based method. They have 200x motion video, and they further chop it into a lot of smaller clips. So they have maybe more than 2,000 samples in the training. So they have a much larger data set, so they can use STGCN more effectively. So I would say there's no golden rule for this. It depends really on how much data you have. But we also have some paper reviewer. They may challenge us on, okay, if you use deep learning, then is it fair to compare with traditional method? Say for deep learning, you have millions of parameters to be optimized. For SVM, how many parameters do you have? Have you tried all the parameters to optimize the SVM-based method, for example? So we also see quite different from computer vision or machine learning paper reviewers sometimes from their point of view. So that's my limited experience on this. Hope you find it useful. Yes.
Thank you very much for the talk. Very interesting. Now, towards the end, you mentioned that sometimes clinicians would look at this and would tell you for example, the arm is being highlighted at the wrong time.
Yeah.
So essentially, you're getting 100% performance, but the model is learning the wrong things to get that performance. That's a very important point, not just for this project, generally for machine learning in general. How do you think? Do you have any plans to address this somehow, to discover where the machine learning model is making these mistakes, and how can we resolve for this?
Right. This is a very tough question. Yeah, we do think maybe the classification method we use is maybe somewhat imposed. I would say it is more like anomaly detection. I would say this is like multi-instant learning is one of the directions we would like to see, instead of assuming that everything will be correct, because we use the label, the overall label for every segment. This is already not quite right. So some segment may really show some abnormal pattern, but overall it is not. So when I talked to one of the clinicians more recently on a grant proposal, so she told me, oh, they will look at the stuff as a whole. So maybe sometimes you will see abnormal pattern, but after all, they will see, oh, this baby is normal. So we may be able to model this by other methods rather than classification. So I think classification, to be honest, it is the starting point, but definitely not the perfect solution.
You need finer grain
Yeah,
labels to do that.
yeah,
That just ring a bell that when people are doing facial recognition or facial things, and they show the attention, etc. on the background, not at the face, and then they do very good classification accuracy.
Good results.
Yeah, very good results. So this is actually a core problem for machine learning entirely.
yes,
So one of the reasons from going for post estimation and using the post information is that the difficulty in accessing basically the videos, and also it reduces complexity a lot. Do you think that, coming back to my previous questions, that the clinician says that having only post information, you have some loss of information? Do you think that an approach of combining post information and pixel information, actually the videos, would be better, or is a good way to move forward, or it causes more problems than it solves?
well, I think definitely the more information we have, the better. Well, we can choose from where we use that or not. So we also think about whether we can have, for example, use the image feature around the joint location to help us to understand more. If we cannot extract the fingers correctly, so maybe we can extract this patch. The image pixel can help us to identify something. So this is definitely something we want to do more in the future. Again, due to the limitation of the data, the RGBD data set, so you can see the CG rendered, basically it is not useful if you try to learn some image feature from this. So this is, but with the RBI 38, we can try to extract some real world image features from the video. So this is definitely something we would like to try.
I guess they're always the same problem of access, limited access to information.
Yeah, it's
From
very
clinical studies.
Yeah. Yes.
Yeah, actually, I recently did some similar research on the competition data side. I found that the current platform for the drawing instruction and also represent some biophysics in Cerebral, and something like the muscle motion and something others. So if this is the issue is your study.
Can you repeat it again? Sorry.
The current platform for the transit instruction,
Right,
may not be able to represent some biophysics in Cerebral. So, and which is I think important in my current task. So, do you think this issue is in your research?
so you meant the backbone is not.
Yeah, maybe
correct.
some kind of platform like the overpause, they just have a PowerPoint.
Yeah.
But sometimes it's interactive and optical, and there are this sort of also have the physical.
Yeah, so for your problem, it seems like you have to look at a much finer level, but for babies, so we just look at these. So the limb level may be good enough. Actually, we find that if we group the feature, the histogram feature at limb level will give us the best result. Part base is not better than the limb level. So from my point of view, it seems like the problem you look into would be much more detailed level in terms of the movement, body movement. For us, for the baby, it's more like very rough limbs movement will be fine, will be good enough. But because as you can see, we just look at the variety and maybe continuity of the movement rather than a specific pattern.
So Sapling, I think there's a possibility that you can use surface model, like what was shown earlier, to estimate the overall baby surface first, and then try to estimate the biologically important joints inside the surface. Now that way you might be able to get a bit more, but you're right. And Edmond also pointed out in the beginning that skeletal joint has a limitation. You cannot represent rotation, say for example, and it's not necessarily biologically correct.
Last question.
Yeah.
So I think in this research, I mean, the clinician more will focus on the safety of your model. I mean, so is that means special criteria if you really want to deploy your model in the real practice?
Oh, that is. I'm glad that I wrote the grant recently, so I know the process. So because they have to ask you the future plan if you want to really deploy it at NHS. It is very complicated. You have to, for example, verify this with a correct cohort size. So this sample is really too small to make any conclusion. So you have to calculate how many patients you need, and also the bias. How do you reduce or minimize the bias of this to make your study meaningful to the clinical usage? And also you have to, if you really say you want to give it to clinician to use it officially, so you have to comply with the standard under NHS. So yeah, the easiest way from my point of view is to work with those software development company, for example, the NHS software provider. So you may work with them or sell your idea to them. This is easier because if you start a company, from my understanding, it's super complicated. Yeah, because there are so many standards that you have to go through a lot of stages. So it is more like you have the idea, you have your own IP that you just share it, sell it, and rather than you develop it.
So Nora's company is essentially doing something like that, right? Knowledge transfer of deep learning for healthcare purposes. Yeah. So this is one of the companies that Edmond mentioned. Yeah. All right, good. We're just about time. So I actually will buy Edmond a coffee. So if you wish to have a further discussion with Edmond or know more about his research or even explore some collaborations, please feel free to join the coffee break altogether. We'll just go downstairs to the cafe. So please, if you wish to have a chat, please join us.
Just another commercial time before you go. So
Okay.
So I'm the award lead for Turing Network Development Award at Columbia University for this year. Basically, it's a around 10-month project. So funded by Alan Turing Institute. So I believe Durham also got one.
Yeah, Durham.
Alessandra also got this award, leading this award. So we will be organizing quite a lot of events. Basically, we try to expand our network. And I managed to talk to, get involved in a regional chat with Edinburgh, Glasgow, Teesside, Newcastle, and Durham. So we are planning to organize some activities together, for example, to understand our research spring and so on. So later on, we will organize some activity, and in particular, well, we have some strong partner through ATI. So we will see, especially what I mentioned, health-related stuff, but not limited to health-related stuff. We can also explore different activities. So if you're interested, do let me know, and obviously we can organize some activities together. Okay, so you know my contact or ask Hubert.
Definitely, lots of opportunities here. Yeah.
Okay, thank you very much for coming.
Thank you very much, Edmond.
Thank you. Thank you.
Feel free to join the coffee, please. Your discussion.